Okay, let's not waste any time. Thought maybe I'll answer some questions, but I thought I could kind of maybe scribble some questions and see if you can review some concepts. Yeah. So many of you probably have forgotten DFAs, so I thought I'll refresh DFAs in the context of algorithms so that you can connect the two, right? Here is a simple question, right? I give you a DFA. So when I say I give you a DFA, basically I give you the description of the DFA, right? So I'll tell you the number of states, I'll tell you the start state, I'll tell you the final states, I'll tell you the transition table. You can think of it as a graph, or you can think of it as a table for every state and every letter in the alphabet. I'll tell you which state it goes to, right? So it's just a table. How big is a table? If I have n states and k is the size of the alphabet, right? The size is n times k, right? Yeah. So if you think of it as a graph, the degree of each node in the graph representing the DFA is k, where k is the number of letters, right? I mean, you can have self loops. That's the difference between our regular graphs and DFAs, is that you could have a self loop, which you have to kind of be a little careful about. Yeah. Okay. So what is the question I'm asking? The first one. I hope it is readable somewhat. That I give you a DFA and I ask, is the language accepted by the DFA infinite or finite? Right? So that's a tricky question in general. If I give you code and ask you, is the language accepted by this code? That's a tricky question, right? But here it's a not arbitrary code, right? It's the most simplest of machines that we studied in this course is DFAs. So this we can hope to answer because DFAs are very simple. We can understand DFA behavior quite well. Yeah. L of M, what is L of M? M is the DFA.
So it's a set of languages accepted by.
No, the machine accepts only one language.
Oh.
Okay. So when I say L of M is infinite, I'm asking, does this DFA accept
A specific infinite language.
Yes. So that means, does it accept infinitely? I mean, does it accept only a finite number of strings, or the number of strings accepted by this machine infinite? How can we tell that? Right. Right. What does the DFA do? Right. What kind of strings does the DFA accept? Okay. Easier question. Do we know how to answer this question if I say, is L of M empty? So I'm asking you, does this DFA accept any string? Yeah. How can we tell whether DFA accepts any string at all? No. I'm saying, okay. No, I'm not asking is it accept all strings. That's different. Right? That is asking L of M is sigma star, right? Here I'm asking is L of M empty or not? Yeah, we have done this before, right? How do you model it as a graph problem, or right? Yeah, that's right, right? A language of the machine is non-empty if and only if the start state can reach at least one accepting state. Yeah? Agreed? Okay. Yeah? We have to be able to reach an accepting state, right? Otherwise, we won't accept any, right? Okay, if you reach an accepting state, then clearly there is a path which takes you from the start state to that accepting state, and that path will define a string, right? That is accepted by the language. Yeah? Is that clear? Okay, but now I'm asking a more difficult question. The more difficult question is will the DFA accept many strings, right? Right? Or will it accept a finite number of strings? Yeah? Alphabet is finite. Yeah, good, right? Why does that have to be the only reason why it should accept many, many strings? Yeah, but as I said, why not? What if I have a cycle, right? Self loop is one example, right? Yeah. So why will we accept longer and longer strings? Why will the DFA accept longer and longer strings, right? So I mean, for example, we have created DFAs to accept the language. We have created DFAs to accept, say, L of m. I mean, L equals, something like. So, for example, we can easily create a. This is a set of, what is this? Just to review regular expressions. What is this language? Any string starts with 0, 0, right? And I can put 1, 0, 0 plus 1 star, or I mean 0 plus 1 star, 1, 0. This is a set of, the string is starts with 0, 0 or ends with 1, 0, right? This is just to review regular expressions. We can create a DFA for this, right? But this language has infinite number of strings, right? So if you try to create a DFA, why will it accept longer and longer strings? Because it must, it is accepting infinite many strings, right? Right. So it should have cycles in it, right? Okay. I mean, if it doesn't have, I mean, okay, but it's not enough to have a cycle, right? So I can give you, I mean, we know any finite language is regular, right? Yeah. So for example, L is 0, 1, 1, 0, 1, 0, 0, 0, 1. This is regular, right? So what does it mean? That given this language, I can create a DFA which accepts only these strings, right? And this is finite, yeah? Okay? So I give you, but I can create the DFA for you, and then I'll give you the DFA and say, you don't know the language explicitly written down, but looking at the DFA, you should be able to tell, that's what I'm asking, all right? You need to develop an algorithm which, given the description of the DFA, think of it as a graph, should decide whether it is going to accept a finite language or it will accept an infinite language, right? So if it's going to accept an infinite language, it must have cycles in it, right? I mean, it's not enough to have a cycle. I can create a DFA which has a cycle but which won't lead to any place. So what should it do? How will you figure it out? Yeah, that is, yeah. So what he's saying is, there should be some cycle so that we can loop around, right? And that cycle, but we eventually have to, the start state should reach that cycle, right? And that cycle should reach the final state, yeah? If that is there, then clearly we'll accept arbitrarily long strings, right? Because from the start state, you can go to that cycle, you can run around the cycle any number of times you want, and then you can go to the final state, yeah? So the self loop is one simple example. He said, these are the path from the start state to an accepting state where somebody on the middle has a self loop. That's a special case of, okay, how will you check that now efficiently? Now the question is it necessary and is it sufficient, right? Yeah, this condition is sufficient. And now you can also convince yourself that it is necessary, right? If there is no such thing, there is no way you'll accept infinitely many strings. But now I want an algorithm. How will you check this condition? You can try all possible cycles, but that is not a polynomial time algorithm, right? So I want an efficient algorithm, learning graph algorithms. How will you check this thing efficiently? What is the underlying graph problem you're trying to solve? Remember, the condition is there should be a cycle such that S should reach that cycle, right? And that cycle should reach T. What does that mean? The cycle should reach T. Some node in that cycle should reach T, okay? And one wrinkle is that cycles could also be self loops. For simplicity, assume there are no self loops. You can think about self loops later, right? You can add a dummy node in the self loop to make it a proper cycle if you want, right? let's not worry about that issue because you have to worry about self loops in DFAs, right? They're really like cycles, but self loops are a little bit tricky. Yeah. See, this is what I want us to avoid. Okay, don't start with DFS or BFS, okay, because then you'll get confused, right? Think globally. What did we learn about the structure of graphs, right? So before you think about algorithms, you say, how will I even know whether the graph has a cycle? What is the structure of a graph you should pay attention to? Algorithms will come later, right? We have many algorithms to do reachability, BFS, DFS, simple search, whatever, right? Before you go down a specific algorithm, think what is it that we want to find? What should the graph look like? And then the algorithms will suggest themselves, right? Because we know the black box algorithms. We don't really care about DFS specifically, right? If I want to know whether there's a cycle, you can do it many ways, but the first thing should not be I should do BFS or DFS, right? Okay, yeah. Yeah, so I mean, if there is no cycle, how will you check, right? Do we know whether, so first, the first thing you have to check is, does the graph have even a cycle, right? Before we know the more complicated things, we should be able to know whether there's a cycle in the graph, right? So how will we check that? That we have an algorithm, right? You don't have to worry about the precise algorithm. I know how to know whether the graph is a DAG or not. Yeah, it could be DFS, but you may not even remember in the exam what is the details of it. But if you start thinking about DFS and mucking around with, should the back edge come this way or that way, you may make a mistake in that algorithm. But if you write down saying, let me check whether the graph is a DAG or not, or we did this in lecture, okay, you're safer, right? But it's also higher level reasoning, right? You're not being stuck on a specific implementation of any algorithm. You're saying, I know how to check there is a graph with a cycle or not. I know even more, right? If it's a strongly connected component, I'm done, right? If the whole graph is strongly connected, the answer is always yes, right? Why? Because the start state will reach, there's a cycle involving the start state, and then everybody is reachable from that. If there's any accepting state, you'll be done, right? So what is the more complicated case? The whole graph is not strongly connected, but then how do we think about the graph then? You should always think about the meta graph, right? You say, so it may not be in a strongly connected. So here is one thing I can have, right? The start state could be here, and there is some cycle, right? And then there is one accepting state, right? Okay. So I mean, this is in a strongly connected component, right? Okay. Yeah, so it's a little trickier, right? So what is the property that you need once you create a meta graph? Yeah. Okay, so I mean, if I give you the meta graph, assume there's only one accepting state for simplicity, right? You can check it for all accepting states. Assume there's only one accepting state. If there's no accepting states, clearly the language is empty, right? Yeah. So let's assume there's only one accepting state, yeah, and one start state, right? So what should we do? So I give you the meta graph. What are we trying to do when we have the meta graph? Yeah. So before we get into this, let's recap what we are trying to solve, right? So we want to know whether there is a path from the start state to there's only one final state for now, right? To this final state, such that we hit a cycle in the middle, right? That's really what we're trying to solve, right? But when you create the meta graph, what happens? The start state may be in a strongly connected component, right? It will be in a strongly connected component, right? It could be itself, but it will be in some strongly connected component. And the final state will be in its own strongly connected component, right? Yeah? So now what are we trying to do, right? We want to know whether there is a path from this strongly connected component to that strongly connected component, which along the way it's a proper strongly connected component. Yeah? Can we do that? Yeah? So it could be that, the start state itself is in a proper strongly connected component, right? In which case we are already happy, right? Yeah? Okay? So that's what we need to do, right? You create the meta graph, check whether the strongly connected component containing the source, or whichever is the start state, can reach the strongly connected component containing the final state, yeah, while going through what? Some proper strongly connected component, okay? So you may not find the most efficient algorithm for this, because if you forget about the topological sort, and you can actually do it in linear time, but the thing you can easily do is polynomial time, right? What you can say is, oh, for every strongly connected component in the graph, check whether the start state can reach that, and that guy can reach the sink node, right? Yeah, I mean, it's not the most efficient, but you're thinking very high level, right? To make sure that you solve the problem cleanly. If you start with BFS or DFS, it is very tricky, right? There's so many moving parts here, right? I need to make sure that the path doesn't, you may get confused, okay? See, the things you need to, before you think about linear time, things like that, you have to say, do I understand what I'm trying to solve in pieces that are at a higher level than just running BFS or DFS, okay? All right? So this is my suggestion, right? Not just for this class and final exam or something. Don't start with an algorithm. Start with the thing that you need to figure out in pieces that make sense at a higher level, so that even if it is not the most efficient, making it more efficient will come later. But you won't make a mistake in what you're trying to solve by trying to adapt details of complicated algorithms like DFS and stuff. Yeah? So you have to keep track. That's your job, right? So you say, strongly connected. I'm interested in a proper strongly connected component. That means it's not a singleton. Okay, that's a detail, right? It's not enough that the strongly connected component can have only one node, in which case it doesn't have a cycle in it. So what you need to do is that you have to mark some of the strongly connected components, and these are good because they have a cycle in them. So you have to call them red or something, right? And say the ones which are not, the singletons are not interesting, right? So you need to go from a source to the sink while visiting one of the red nodes, where a red node is one which has at least two nodes in its strongly connected component, right? Okay. So see, these are details which you need to think at a high level rather than worry about DFS, right? I'm sure there is some DFS based algorithm which is also correct, right? But by the time you figure it out, you will make so many mistakes, right? It's hard to keep all the details in your head straight, right? While modifying something like DFS, right? So typically, you have to think about reachability, right? Yeah. So there was a question on the exam, the midterm. How do you check whether there's a cycle involving an edge or something like that, or a node, right? The idea there is not to try to adapt DFS, right? But think, when is there a cycle? Okay, there's a cycle if from you, I can reach somebody that can come back to me, right? So you're not thinking about DFS, right? You're thinking, why is there a cycle in the graph containing this node U? You first check reachability from you and say, okay, if anybody that has an edge to me is reachable from you, then there's a cycle, right? Then you have reduced the problem to reachability. You're not thinking about DFS. You can use DFS, you can use BFS, you can use whatever, right? Yeah. So that's the thing that I would advocate. Okay. Any question on that? Yeah. I just wanted to make sure that we touched upon DFS just to but along the way you should hit a proper strongly connected component, right? So at least two nodes. But then there's a small technicality is that, you know, a node which has a self loop also counts. So it's more work. Okay, I mean, if you do, so you have to mark those guys also as red. Okay, so yeah. What will be a linear time way of doing that? You should do the topological sort, right? And keep track whether you have reached anybody in the middle. Okay, that's a good thing to think about. Figure out how to do it in a linear time using topological sort. Yeah. Okay, good. Okay, regular expression from what? The DFA. That's a bit difficult to understand, but let's see. But how will, I mean, it won't be efficient though, right? Well, you know, we did, I mean, we briefly did this conversion of DFA to regular expression using Floyd-Warshall algorithm. Did we do it? I don't think we did it. We didn't do it. But it actually creates exponential size regular expression. That's why it's not very good, right? The graph to the DFA to regular expression blows up the size of the regular expression. It's not going to be efficient. Yeah. Yeah. Okay. So let me ask that related decidability question, right? Okay. What do you think? So what is that? What is the language? What am I asking? No, it's not languages. What is that I mean, whatever that. What does that mean? What is this? So it is the set of all descriptions of machines, right? Such that the machine is actually a DFA and is an in actual no strings. Yeah. Is that language? So what is that language decidable? Yeah. I mean, so this is the same problem that you're asking, right? You know, given a DFA, can we check whether its language is empty, right? In fact, we have a linear time algorithm for this, right? So it is clearly decidable, right? Okay, but I mean, I just, you know, I'm trying to create trick questions for you so that you. So if I say, I mean, when we think of is that decidable? It's not decidable, right? That's asking about full code, right? You know, it's not a DFA. DFAs are very simple programs. We can figure out lots of properties of DFAs. But if I give you an arbitrary program, we cannot decide, right? Yeah? No, not every DFA. No, there's no notion of DFA being decidable. See, this is a language whether it's decidable or not, right? So what is the first? I mean, what is the first problem? The first problem is asking, you know, if I give you the input to that problem is a description of a DFA, and you have to check whether the language accepted by the DFA is empty or not. That we can do, right, by graph reachability because it's a simple machine. It's not because only finite number of states, because we know how to do it, right? You know, we understand the behavior of DFA very well, right? We have an algorithm, right? Check whether the start state can reach any accepting state. That's an algorithm to check whether DFA accepts empty strings or not, right? While for a code, it is not possible. If I give you arbitrary code, reasoning about code is hard, while reasoning about DFAs is easy. Yeah. NFA. What about NFA? But it's still decidable, right? Yeah, right? It's not, we're not asking is it in polynomial time. We're simply asking is it decidable? Is there any algorithm at all, right? And that's clearly decidable. What about CFG, though I know it's not on the final, right? If I give you a CFG and ask is L of CFG empty? Okay, that's a little trickier. Let's not go there, but it's not very hard actually. If I give you in a Chomsky normal form, it's not hard. Actually, it's a cute question. You can, it's a simple question, but let's not worry about it. We have to go into CFGs now. Okay, so what I'm trying to say is that, see, if you make the machine complicated, the class of machines you're trying to understand complicated, clearly the problem is going to get harder, right? Yeah. So that's all I'm saying. You know, DFAs are very simple, so we can reason about them. So that's why people want to write simple programs, right? So that we can actually verify whether what we are trying to do works or not. If you write complicated programs, reasoning about them is hard, right? So in a simple setting, that's okay. Okay. Any questions? I mean, I thought I'll review a couple of things. Okay, here is just to some NP completeness. So very simple one. I give you a graph G and an integer K and ask, is there a path of length at least K in that graph? Is it solvable in polynomial time or is it NP complete? Yeah. I mean, I'm a bit worried that it's taking surprisingly long to answer this. Right, you know, yeah. I mean, I actually even mentioned this problem explicitly in shortest path lecture. Why can we not solve shortest paths with the negative edge lengths if you want simple paths? Because I said we can solve the longest path problem. If you can do that, and somehow longest path is hard, and we'll figure it out when we get to, right? Yeah, what is a special case of this problem? Yeah? Or the other way? Okay. Right, if you can answer longest path, you can solve Hamiltonian path problem, right? Okay. Hamiltonian path problem is what? Is there a path of length n minus 1, right? So if you can answer this, is a more general problem than Hamiltonian path, right? It's saying, is there a path of length k? So its input it has two inputs, right? G and k. So I can give it G and n minus 1, and the answer is yes, I know that graph has a Hamiltonian path or not. Yeah? It's a more general problem than Hamiltonian path, right? Yeah? So that's why it's NP complete, right? Right? Okay. Is it clear? Okay. Okay, what about shortest cycle? Oh, so I should say, yeah, shortest cycle, and it is not well specified. Okay, there are two versions here. One is with the non-negative lengths and one with negative lengths, potentially negative lengths. Suppose I say they're non-negative lengths. The lengths are not negative, cannot be negative. Yeah. Directed graphs. Metagraph only tells you about the structure of whether there are cycles or not, right? It doesn't tell you lengths. If I give you lengths and no, but if whatever is only one node in the metagraph which is strongly connected, right? Then you're still in the same problem. Yeah, it's really about strongly connected graphs, right? It was even a problem in the homework. I mean, it was an extra question, which problem very good actually. Yeah. I mean, how can you reduce Hamiltonian cycle if the lengths are non-negative? If the lengths are negative, yes, you can reduce Hamiltonian cycle to this problem, right? Yeah. See, if the lengths are negative, shortest path cycle is the same as longest cycle, no? Yeah. I can take all the edges and make them -1. Then finding the shortest cycle in a graph with negative lengths is what? All the edge lengths are -1. What is it? It's find the longest cycle, no? But from the previous reduction, we know if the lengths, if you want to find the longest cycle, that's the same as it's a more general than finding the Hamiltonian cycle, no? Yeah. So you can solve Hamiltonian cycle if you can solve shortest cycle with negative edge lengths, right? But suppose I don't allow you negative edge lengths. Yeah. No, I'm saying that if I ask you shortest cycle in a graph with edge lengths can be negative or positive, so I can do the following. I take an arbitrary graph which is a regular graph with no lengths, make it have -1 on each edge, and then say find the shortest cycle in this. That's the same as finding the longest cycle in the original graph which has positive edge lengths, right? But then that would allow us to solve Hamiltonian cycle. Okay. But what about shortest cycle if I don't allow you to have negative edge lengths? Again, don't overthink, right? Look at your midterm 2 problem. How did you figure out whether there was a cycle involving a vertex? If you I see many of you solved that problem.
Well, you're trying to see if there is a way to get back. Like if you don't use
Yeah, what if you wanted to find the shortest cycle involving a vertex given vertex u? No, see, you cannot, I mean, the only way you can find shortest paths is by Dijkstra's algorithm. Or some algorithm, you know how to find shortest paths, right? See, so, okay, so let's see, we want to solve, see, we break up the finding the shortest cycle problem into the following problem. For every vertex, find the shortest cycle containing that vertex and take the best. Yeah? That makes sense? Okay, now you have to solve the problem. Given a vertex, I want to find the shortest cycle containing that vertex. How will you solve that? So that's so let's look at this vertex u. How does a cycle involving this vertex u look like, right? It consists of a path from u to some vertex and one edge from that vertex back to u, right? So you find the shortest path from u to every vertex, yeah? That you can do using Dijkstra's algorithm, right? And then look at u and compute for every incoming edge the length of the path from u to that vertex plus the length of that edge from this, and among all those pick the one which is cheapest, right? It's the same as finding a cycle involving u, no? Except that we want to find it shortest. So what will you do? We reduced the problem of checking whether there is a cycle involving vertex u to a reachability question, right? A path problem. Okay, so now instead of finding the reachability, we are using shortest path from u to everybody, and then looking at the last edge and saying, we add that edge length and that path from u to that vertex, and among all those things, take the minimum. That will give you the shortest cycle involving vertex u, right? And now you do it for all vertices, and you will get the shortest cycle. Yeah? N times, not constant times, n times you'll have to do Dijkstra's cycle. Right? So it's like solving all pair shortest path problem, right? You can do another way of doing it is I find all pair shortest paths, right? Okay, and for every edge you check, what is u to v, you check the shortest path distance from v to u plus uv, that will give you that's another way of doing it, right? Solve all pair shortest paths and then do one pass over each edge. Yeah? Is that clear? So again, I don't want you to think too much about efficiency before you understand the structure of the problem, right? So what's a cycle? I say a cycle is a path plus an edge. So I know how to compute shortest paths. I don't know how to compute shortest cycles, right? If I told you shortest paths, you would say, yeah, I know how to do it because I have learned Dijkstra's algorithm, right? So why don't people talk about shortest paths, cycles explicitly? Because they know you can easily reduce it to shortest paths, right? So they don't always explicitly talk about shortest cycles simply because they know it can be easily reduced to shortest paths, right? So that's the reason why we ask those questions, because then you're checking whether you can decompose those things or not, right? Okay. Okay, now maybe I'll let you ask questions. I just wanted to review some basic things. Decidable. So I mean, just to know, I mean, you will have a question on undecidability. It's clear, right? You will have a question on NP completeness, okay? Because they are important topics that we covered in the last section, right? Something on reductions, including decidability, NP completeness, they are important topics, right? And something on algorithms, shortest paths, reachability, dynamic programming, right? Yeah. Sorry? Oh, reduce Hamiltonian cycle to Hamiltonian path. Both ways are possible. Both are interesting problems, right? Okay. Yeah, you can do both. Oh, sorry, you said. Oh, first question. What are you trying to prove is hard? Okay, if you want to prove longest path is hard, how can you reduce that to something which is hard? You have to reduce something to it, right? Yes. Okay, but try reducing the other way. Is it easy? Well, no, okay, tell me how you'll do it. Okay. Okay, see, longest path has two parameters, right? It's trickier. The graph might not have a Hamiltonian path, right? But it could have a path of length k, right? How will you know if I only gave you a black box algorithm which only checks Hamiltonian path? No, it's not easy actually. Okay. So okay, here is the thing. If I want to reduce longest path to Hamiltonian path, it's not easy, no? See, longest path is asking the following problem. Given a graph and some integer k, is there a path of length k in this graph? But Hamiltonian path will only answer, is there a path of length n minus 1? It's not going to answer given k, right? It doesn't have any input like k. It only takes the graph as input. So if you want to know whether the graph has a path of length 100, how can you solve it using a Hamiltonian path problem? We know we can do it because it's also NP complete, right? You know, that's funky, right? There exists a reduction between longest path and Hamiltonian path because Hamiltonian path is NP complete, which means that every problem in NP should be reducible to it in polynomial time. That doesn't mean that you can come up with it on the fly or easily, right? So one way to do it is if you can reduce longest path to SAT, and then we know how to reduce SAT to Hamiltonian path, right? I mean, that's an easy way of, but it's not obvious how to reduce longest path to SAT first, right? Okay, because the k is there, right? K is always funky. Okay, you can say, okay, I can write code to check whether longest path has, right? So all I'm trying to say is that it's not obvious, but there exists a reduction which is complicated, right? The easier direction is to reduce Hamiltonian path to longest path because the longest path is a more general problem than Hamiltonian path, right? You can easily. So that is also the reduction you would use to prove that longest path is hard. Okay. Is that clear? So always, if you want to prove something is hard, that should be on the thing that you should reduce some existing hard problem to that problem, right? Otherwise, you won't. Like that's one reason why I gave that example in the homework on why reducing perfect matching to SAT. It doesn't prove that perfect matching is hard, right? Perfect matching is actually easy. It's in polynomial time. I mean, we didn't discuss that in the class because it's a more advanced topic. But perfect matching can be solved efficiently in polynomial time. Okay? SAT is hard and be complete. So clearly SAT can model perfect matching because it's a richer problem, right? So reducing perfect matching to SAT doesn't tell you anything about perfect matching. Okay. If you reduce SAT to perfect matching, then you will know perfect matching is hard. Okay. But we don't think that will exist because we know perfect matching is easy. Okay. All right. So you always have to think, what am I trying to prove is hard and where should that be, right? Yeah. Okay. Anything else? Okay. Hamiltonian cycle to Hamiltonian path. Yeah. You want to ask question or do you want to? Yeah. So think. Do you want to think for a few minutes? Yeah. Before you.
If your original graph had tapers, right? If the original graph had if the original graph has an Hamiltonian cycle tapers, which means total graphs, then you say if there's this tape that tapers in the original graph,
Yeah. Hamiltonian. Yeah.
cycle of tapers graph will have the Hamiltonian path in the one versus the new back on the new vertex of an existing and track every vertex in the original graph.
Is kind of in the right direction. So I want us to think. So when we're doing reductions, right? Okay. So okay. So before we discuss his solution, so why is this a little? I mean, so I want us to think a little bit about why the reductions, how to think about reductions, right? So if I try to ask you to reduce Hamiltonian cycle to Hamiltonian path, what are you trying to do, right? Right, they look similar, right? But the black box for Hamiltonian path will only answer yes or no if the graph has a Hamiltonian path, right? That's a restricted algorithm. It only will say yes or no if there's a Hamiltonian path, right? But you want to check if the original graph has a Hamiltonian cycle. But clearly, if the graph has a Hamiltonian cycle, then there's a Hamiltonian path, right? So, but be careful, right? The graph can have a Hamiltonian path and not have a Hamiltonian cycle, okay? So you have to be clever, right? You have to know the right answer even when the graph has Hamiltonian path but no Hamiltonian cycle. So if you take the original graph and give it to the Hamiltonian path algorithm, it may say yes, but the original graph may not have a Hamiltonian cycle. Yeah? So you have to be a little bit careful in how you set up your problem, right? Okay. So I'll let you think offline, post on Piazza if you want. But if you have any other questions that you want to discuss, I'll be happy to answer them. Yeah? Yeah. So just the definition more or less that okay, what is the meaning of Turing machine? That it's a tape, right? You can move left or right one step, you can when does it accept, when does it reject, right? There is nothing very detailed, but you do need to know the definition that it has states, it has tape symbols and input symbols which can be different. The tape symbol always has blank, right? That it can move left and right or stays put, right? The basic definition. I mean, not that we are going to ask intricate questions about that, but you may ask something which may be a short question, which is sort of, if you don't know the definition, you may run into some trouble, right? Yeah. Oh, here is another interesting question, which I think was there in last semester's homework. I was almost tempted to give it, but then didn't, right? It's a tricky one, but it's a cute one. So, okay, I give you a DFA, right? And I give you a string in sigma star, right? A, B, D, okay, whatever, right? Some long string, right? So the input is, let me just say, no, just W belongs to sigma star, right? So the input is DFA and a string, or a subsequence it combines three things, or in some, right, you know. Is the problem clear? Okay, I can, yeah. So, okay, so let me try to give you an example. Okay, trying an example will be tricky. Maybe I'll pull it up, but in the meantime, can you try to understand that problem? What is it saying? So I give you a DFA and a string, right? If the DFA accepts that string, great, right? Maybe the DFA, I mean, then that's the longest subsequence that of that string that DFA accepts. So I mean, the interesting case is DFA doesn't accept the string, yeah. So, but you want to find the longest subsequence that is accepted by the DFA, yeah. Okay, yeah. I mean, so what technique will you use just to get a quick sense, yeah? The third one, okay. Not, I mean, no, I mean, I guess, you know, just two things maybe, right, you know. It's DFAs and no, dynamic programming, and right. Yeah, it's not an easy question. I mean, I wouldn't ask this in an exam, right? But it's a nice homework question, right? But if you want to kind of review DP and DFAs, this is a really nice question. Yeah, I mean, let me pull up some examples so that it's a little less abstract. It's a nice, very cute question, I think. Homework 5. Is this homework 6? Oh no, maybe it's not from last, or maybe it is from one of our old exams. Oh, I see. It's not from fall 16, but trying to remember what is one of my old courses. I'm confused now. No, I don't. Yeah, not sure. Okay, I may not be able to create a nice example for you. Let me suppose even the DFA could be this, right? Let's see. So what language does this DFA accept? Sorry? Yeah, it'll accept odd length strings, right? Yeah? Okay. So, I mean, so I can give you this DFA, and I can give you a string which is of even length, right? So I can say 0, 1, 0, 1. Then your answer should be 3, right? Yeah, you know, there are many possibilities, but you say, okay, you know, I can find, I mean, this is just a very simple example, right? See, this string is not accepted by the DFA, right? So you have to figure out that, okay, I mean, You have to do it automatically. You can't just look at this DFA because the DFA is very simple, right? So it could be the DFA could be very complicated. The string could be very long, right? So your algorithm should handle any DFA and any string, right? So it's right, yeah. So I mean, it's enough to know whether after reading the first I letters of the string, what are all the possible states you could be at? Right, that's one way of doing, right? You know. No, that can be exponential because you will remain subsets, right? So, so you can say this, right? So here is you can say it, you know. I don't think of it. Let's see. You remember you I have to think of it a little bit. Yeah, this is a tricky one. So, so you can do this, right? You can say T Q I J is 1 if there exists a subsequence of W1 to the, I mean, this is the first I letters of length J that takes M from S to Q. Okay. I mean, this is not the most efficient, maybe. I just thought of it, right? So you say, okay, you know, yeah. You can do other, yeah. This is you can do product construction also. Yeah, so there are many ways of doing it, right? One way of doing it is this, using DP, right? But you're basically you can use a graph construction, right? So, for example, how would you use a graph construction for this? Yeah. Well, longest path is hard, right? No, that was we are just proving it is hard, right? Longest path is hard. Shortest path is. So here, you know, it's also we can skip letters, right? We're not finding the substring. We're finding a subsequence. That's more tricky. Substring is, you know, that we want. If I just substring, it's very easy, right? Substring means that, you know, I have a string of this and I want a contiguous piece, right? I can try all possibilities then, right? I can take that substring and check whether the DFA accepts that substring or not and find the longest one. I'm not interested in finding substrings, right? I'm interested in subsequence. So it could be that my string is, and then I take this guy, this, and this, and that is accepted by, that is the string that is accepted by the DFA, right? That's different from, I'm allowed to skip. How will you reduce it to a DAG problem, by the way? Is when you're doing product construction, so you can reduce it to a DAG problem. You can try to reduce it to a DAG problem, right? So layered DAG. You can remember you can solve longest paths. If you think of longest paths, you should say, I can do longest paths in DAGs, right? Yeah. Yeah. Yeah, you can do that, right? You can create n copies of the DFA, right? And you make sure that one copy to the next copy, you follow the transitions, but you have to allow for skipping, right? So what does it mean to skip? Skip means it goes off into some dead state, or not dead state, but I mean, if it skips, you have to make sure that, so you have to implement skipping. Yeah, you can do several tricks, okay? But you can also do the layering, right? You can create n copies of the DFA, and going from one copy to the another will correspond to a transition, right? And you have to be a little careful about the skipping, right? So there are many, see, there's a close connection between dynamic programming and DAGs, right? Okay, so many dynamic programming problems you can instead solve directly via graph reduction. Right? You are doing product construction, which is more or less, again, similar concept as creating this many copies of the graph, right? So they're all related to each other, right? Yeah. This is a tricky one, but I'm just trying to say that why DP is powerful, right? You can talk about this kind of problems, right? First, it's showing that DFAs are easy. You can solve many funky problems with DFAs because we understand it, right? And DP is also powerful, right? Yeah. Yeah, a little bit. It could be that the layered graph approach sometimes gives you less efficient algorithms unless you go back and optimize it. You say, look, I don't actually need to actually create all the layers because I only need 2 layers at a time, right? You have to explicitly do it, right? Or sometimes the space is more because you have to create all these edges of the graph, even though you may not need all that information dynamically, right? So the important thing is to first figure out a correct solution, even if it is not the most efficient, right? Don't let the running time thing first guide you into some path where you say, I have to use DFS because I need linear time, and then you lose track of what you're trying to solve. Yeah. So that's very important, right? First try to say, what is the structure of the problem I'm trying to solve. Yeah. No more questions? You're okay? Yeah. What is the structure of the final? I don't. I mean, there are some problems, you solve them, right? I don't know. It's 3 hours, right? No, there's not particular structure. You can see from there will be about like either 6 or 7 questions depending on how they're broken up. And that's about it, right? I haven't decided the final yet, so I have no idea, right? Roughly, yeah. It will be half an hour per problem or 25 minutes, something like that. Right? Yeah. That seemed okay, right? So the second midterm had 5 problems, so 2 more problems, right? It's between 6 and 7. Right? We also have to grade them, you see. That's also a constraint, right? The more problems we give, the more we have to grade, okay? And we have to do it quickly, right? Reductions are okay. 2 is important, right? If and only if is important. Yeah, yeah. Well, I mean, the thing is, you know, it, I mean, it is good to keep track of one canonical reason why some language is not regular, right? You know, why is a language not regular? What is the limitation of the DFAs, right? The limitation of DFAs is that what? It's only finite number of states and there's no tape, right? So if there's no tape and all your memory is finite, then basically you cannot do any task which requires you to store some kind of information, right? So that's at a high level something that you should remember. The formalization of that is via fooling sets, or you can do it from first principles like pumping lemma or something like that, right? You can sort of do it by proof by contradiction, right? You say, oh, look, you know, if I have a DFA with n states which accepts this language, I can fool it. You don't have to remember fooling sets to kind of start that reasoning, right? But you know, the formal argument requires thinking a bit more carefully and understanding that. So I didn't want you to. It takes some time to absorb that again, even though it's intuitive. So I removed it mainly to give you a little less to remember, right? But non-regularity is useful and important. That to what is a canonical non-regular language we discussed? The 0 to the I, 1 to the I, right? I greater than equal to 0. So that's the simplest thing which tells you that if you don't keep track of the number of zeros, you cannot match up the ones, right? So the finite state machine cannot count, right? Because you can increase the size, but it has to be fixed at some point, right? And then say, okay, then I can fool it with the longer strings, right? So that's more or less at the level at which you should kind of remember. Yeah. Mm-hmm. Yeah, we didn't really do that. So, I mean, here is a simple, I mean, maybe, I mean, just for fun, if you want some closure properties, right? Let me ask this question. It's pretty simple, but okay. What do you think? I mean, this is just knowing what decidable means, right? And what is the operations, right? What is it saying? L1 is decidable. What does it mean? It means there is an algorithm which will correctly, right? L2 is decidable. So we also have an algorithm for L1. So do we have an algorithm for L1 bar? Yeah. Yeah, we run the algorithm for L1 and flip the answer, right? Remember, it's an algorithm, right? Properly runs, right? It gives you the right answer, right? So you flip. What about L1 union L2? You run them, what? No. Remember, it's decidable, right? We are talking about code. It is not DFAs. You can't do product. So you run them both, right? And if one of them accepts, you accept, okay? L1 intersection, you run them both, right? Okay? And all of them are decidable, right? Decidable is nice that way because it's just you run them, right? So here is a more tricky question, which we didn't do, but just yeah, all of them are decidable, right? Because that's the nice thing about algorithms; they're nice to compose. Okay. Sorry. Yeah, like regular expression, except you have to be little careful because here it's so general that it's nice to everything is closed, but regular expressions you have to think more, right? Because they're restricted programs. Flipping the answer is not obvious for a regular expression, right? But we can flip because we know for DFA it's a characterization, different characterization. Right? It's not obvious that regular expressions are closed under complement, right? The way we define it is not obvious, but then we say, because it's easy to complement with a DFA and the equivalence, we can figure out that regular expressions are closed under complement, right? It's more difficult, right? At this level of code, at, just high level algorithms, it's easy to flip the answer, right? The code can easily flip the answer. But what about this? L1 is, I mean, we didn't cover this much, but just for, right, recursively enumerable. Then it's a little tricky. Okay. What about L1 bar? Oh, I mean, it's what does recursively enumerable mean? No. Recursive means decidable. Recursively enumerable is a little bit even bigger, right? Yeah, I mean, not bigger, I mean, that it's a weaker notion, yeah? Yes. No. It's not all thing, but it's a definition. What is the definition of recursively enumerable? Yeah. Yeah, that there's a Turing machine which will accept strings in the language, right? Halt and accept strings in the language, but what about strings not in the language? It may not halt, right? Okay, but if it halts, it will reject, right? But it may not halt, right? So that's a kind of a weak notion. So what about L1 bar? Can we say something about L1 bar? Yeah. Yeah. So it's a subtle thing. In fact, L1 bar, okay, so let's think about it like this, right? So this is recursive and this is RE languages, which are bigger, right? And outside is stuff which is not even recursively enumerable, right? Okay, my claim is that if L1 is here, what is complement of L1 bar, L1? If L1 is here, L1 bar also has to be here, right? We just discussed that, right? If L1 is decidable, L1 bar is decidable, right? Because we have an algorithm for L1, we can flip its answer because it always halts, right? And gives the right answer. That's what it means to be recursive or decidable. But if L1 is here, then what happens? Where is L1 bar? Yeah, it cannot even be in RE actually, it has to be outside. It cannot be, clearly it cannot be inside, right? Because if it is inside, its complement would also be inside, right? Right. Okay. So I claim L1 bar has to be outside. Why? If L1 bar was inside RE, so it's what I'm saying, if I know that L1 is recursively enumerable and L1 bar is also recursively enumerable, then actually it is decidable. Why? No, it's not the definition. No, it's not true. You have to be a little more careful. Yeah, no, but tell me a machine which decides that. So you have to run it in parallel. Okay, that's important. Okay, remember if L1 and L1 bar both are recursively enumerable, that means they have two machines, right? One for L1 and one for L1 bar. Okay, so on any input you have to run these two machines in parallel. What does it mean to run in parallel? You have to, step by step, you have to run them in parallel, and you're guaranteed that one of them will halt and give you the right answer. Okay, if you run sequentially, it's not going to work, right? If you run the machine for L1 on W, maybe it will not halt, right? It's true that either the machine for L1 or the machine for L1 bar will halt, but you don't know which one. So you can't run them sequentially. You have to run them in parallel. Okay. So if L1 and L1 bar are recursively enumerable, then actually L1 is decidable. Okay. It's a tricky one. Okay. I didn't do it. Yeah. All right. So recursively enumerable is a complicated concept. So let's not worry about it. Right. I mean, we didn't dwell in it because it's not as natural and it's trickier. So, but I just thought I'll do it. Outside of RE means that we don't even have a machine that will accept strings in the language. Okay. In fact, there are plenty of language by diagonalization, everything out. I mean, in fact, the complement of remember what is remember LU? What is LU? LU is MW such that M accepts W, right? This is recursively enumerable, right? Why is it recursively enumerable? Because I can run the code of M on W and check and wait, right? If it accepts, I say yes, otherwise I can simulate, right? Universal Turing machine will simulate M on W. And what is the complement of this? Yeah, but that is not even recursively enumerable. How can I tell, given code in W, that it will not accept it? You don't know. How will you know? So see, so what is the complement of LU? It's all strings which are encodings of Turing machines or code and strings such that M does not accept W, right? So how will we know that M does not accept W? We can't tell because even if we simulate, we won't know whether it will stop or not, right? Okay. So the complement of LU is not even recursively enumerable, right? So it's a tricky concept because recursively enumerable says that if only for things in the language you have to stop, and let's not worry about it, right? It's a little trickier concept. Recursively enumerable is mainly of interest to theory people, right? But also because it is a tool, right? It's a tool to the universal language is what allows us to prove undecidability. But let's not worry, it's a little tricky. Okay, we stick with decidable because we know they are related to algorithms, right? Yeah. All right. Okay. All right. Good luck. And tomorrow's lab is review or office hours. If you are interested in talking to the TAs about something, you can do that. I will probably move my office hours from Friday to Thursday because some of you probably have exams and I have some other things to do on Friday. So I'll post on Piazza. Okay.
No.
Enjoy.
So